In this video, I'm going to show you how to take derivatives of basic exponential functions with linear arguments. Here's an example of a basic exponential function with a linear exponent, 4x minus 1. So how do we take the derivative of this? Well, we know from before that the derivative of e to the x is just itself, e to the x. So let's use substitution and the chain rule to change this problem into something that's similar to this derivative which we already know. So the trick here is going to be replacing this 4x minus 1 with u. We're going to lump that 4x minus 1 expression into a single variable, u. So the derivative will now read d over dx of e to the u inside. Okay, so now how do we take the derivative of this? It's kind of similar to the thing we know, except we're taking derivative dx with respect to an expression of u. So how do we reconcile the difference in variables here? The answer to that is to use the chain rule. So we're going to go ahead and write this as d over du of e to the u, and the chain rule just says that we are allowed to do that as long as we multiply by du over dx at the end. It's kind of like the du's cancel out and we just have d over dx. So we have an equivalent expression, but now we can go ahead and take the derivative here with respect to u. And d over du of e to the u, we already know that's just e to the u. Now to find the du over dx term, we can look back to our expression for u equals 4x minus 1, and we can just differentiate that with respect to x. So du dx is just the derivative of 4x minus 1. The derivative of 4x is just the coefficient on the x, which is 4. And then the derivative of minus 1 is just 0, because that's a constant. So du dx is just 4, the coefficient on the x. So we'll write that here, e to the u times 4. And now we'll go ahead and substitute back for u. We'll write this expression in terms of x, because that's the variable we had at the beginning. So let's move the 4 out in front. So it's 4 times e to the u power, and u is just 4x minus 1. So there we have it. There's our result. That's the derivative of e to the 4x minus 1. So if you look closely, you'll see that this 4 in front really just came from this 4 in front of the x here. We just took the derivative and found that the derivative of the linear expression was 4. And that leads us to a kind of general rule for finding the derivative of an expression e to the px plus q, where p and q are constants. The result is that we just take that coefficient on the x, the p, and move it in front of the e. So it becomes p times e to the px plus q. So that coefficient on the x just gets moved in front of the e and ends up multiplying the existing e to the px plus q. Now, one caution to this general rule is that it only works for arguments of the form px plus q. It only works for linear arguments, for linear exponents. So that means that if we have something of the form, say we have an expression e to the x squared, and we want to take the derivative of it, we can't use this rule, because x squared doesn't match up with an x. X squared is a quadratic exponent, not a linear exponent, and this general rule only works for linear exponents. But we can still do this using the chain rule, which we'll see later. But for right now, we're going to focus on this general rule and apply it to take derivatives of exponential functions with linear arguments. Let's use that general rule to take the derivative of this exponential function without actually going through all the steps of making a substitution and applying the chain rule. So our first step is to move out this constant outside of the derivative so that we can actually use our general rule. we just want to get the e to the negative 2x plus 7 by itself, because we know how to take the derivative of that. So we can just bring the 3 outside, write it as 3 times d over dx of e to the negative 2x plus 7. Okay, now we can use our general rule to find the derivative of this single exponential term. And the general rule just tells us that the coefficient of the x for a linear exponent, this is indeed a linear exponent, and the coefficient of the x will come down and multiply the e. So we're going to have 3 times the negative 2 is going to come down and multiply the e to the negative 2x plus 7. So now we can go ahead and simplify. 3 times negative 2 is just negative 6, and then we've got our e to the negative 2x plus 7. There we go. There's our result. That's the derivative of our original expression. Now let's consider the case when the base of the exponent is no longer e. So here we want to take the derivative of 2 to the 7x plus 3. The base is 2 instead of e. So how do we approach this problem? Well, we've got a rule that we know for taking the derivative of any number a raised to the x power. That's just a to the x plus natural log of a. So let's use the same process as before to reduce this problem to using this rule in conjunction with the chain rule. So first of all, we're going to lump this 7x plus 3 expression into a single variable, u. We'll set u equals 7x plus 3, and then our derivative will become d over dx of 2 to the u. Now, our variables don't match. We're taking derivative with respect to x, but we've got an expression of u. But as we saw before, we can fix this problem by just using the chain rule. So we'll just take d over du of 2u, and chain rule says that we can do this provided that we multiply by du dx at the end. So the du's cancel, and it's equivalent to what we had before. So now the problem just reduces to applying this derivative rule to compute d over du of 2 to the u, and then finding the derivative of u with respect to x. So let's start out just applying this rule. Here a is 2, and the result is just 2 to the u times natural log of 2. And then du dx, we can look to our expression for u here, taking the derivative with respect to x. Derivative of 7x is just 7, and derivative of 3 is just 0 because 3 is a constant. So du dx is just 7, and we'll plug that in here. And now we can go ahead and simplify our expression and substitute for u again in terms of x. We want our answer in terms of x because that's what we started with. So we'll move the 7 in front, so 7, and then we'll put the 2 to the u part, but instead of writing u, we'll write 7x plus 3. And lastly, we've got our natural log of 2 at the end. And there we go. There is our solution. That's the derivative of the expression we started with. And this leads us to a general rule. In general, the derivative of some number a raised to a linear power, px plus q, is just p, the coefficient on the x, times a to the px plus q, which is our original expression, and then times natural log of a. So this is kind of similar to the general rule from before. The p, the coefficient on the x, hops out in front of the a. It multiplies the original expression. But now we've got a natural log of a at the end here. And you can make sense of the previous general rule because when a is equal to e, then the natural log just comes out to 1, and we've got the same rule as before. So again, one caution to this general rule is that it only works for exponents which are of the form px plus q. It only works for linear exponents. So in concrete terms, what that means is that if we've got an expression 2 to the x squared, and we want to take the derivative of this, we can't take the derivative using this general rule. We can still do the substitution and chain rule procedure, as we'll see later, but this general rule where we bring down the p and multiply by natural log of a doesn't work on 2 to the x squared because x squared is a quadratic argument, not a linear argument. For our last example, let's use those general rules to take the derivative of a large exponential expression without actually going through all the steps of substituting and using the chain rule. We want to do this very quickly. So our first step is to notice that we've got two terms in here, and we can just differentiate them separately. We can start off taking the derivative d over dx of the first term, a half e to the 4x minus 3, and we can also pull out that a half in front of the d over dx, so we just isolate the e to the 4x minus 3 part. And then we can go ahead and add the derivative of the second term here, so plus d over dx of that second part, and here we've got a coefficient of 2. In order to isolate the exponential part, 7 to the negative 5x plus 6, we can move that 2 outside the derivative. So plus 2 times the derivative of 7 to the negative 5x plus 6. All right, so now we're good to go ahead and apply our rules here. So for this expression, for the base e, we just moved this 4 out in front. So that's just a half times 4e to the 4x minus 3. And then for the other expression, it's pretty similar. The general rule for any base a is pretty similar to the original base e rule. We move out the x coefficient in front, so 2 times negative 5 times 7 to the negative 5x plus 6, but the only difference is that also we have to multiply by the natural log of 7 of the base at the end. So we can go ahead and simplify the expression now. Half times 4, that's just 2, so 2e to the 4x minus 3, and then 2 times negative 5 is negative 10, so negative 10 times 7 to the negative 5x plus 6 times natural log of 7. And there we go. That's the derivative of our original expression, and we didn't even have to make any substitutions or use the chain rule. In the future, we'll learn how to differentiate even more complicated exponential functions.